Well, we've got a recording of these pucks moving around. Let's have a look at them moving in slow motion. Now, the time interval between successive frames is exactly 1/25th of a second, so that the ones that travel furthest in between slow motion frames are the ones that are traveling fastest. In fact, the distance traveled is proportional to the speed. I can estimate the range of speeds in our collection of pucks by seeing how far each puck moves in a given length of time. Incidentally, I don't have to worry about directions because I'm interested in speeds, not velocities. If I now collect all the lines together, I can readily group them into a series of bands according to their lengths. And so I can count the number of pucks that have speeds falling into each of these bands, and then I can plot this information to show the distribution of speeds among the pucks. Of course, my statistics are still small, but if I repeat this process many times using lots of successive frames, then the distribution gradually smooths out. And I can represent it by a smooth curve. Well, what are the most important features of this solid curve, which is the distribution of speeds we've just got for the two-dimensional puck model? You can see that there aren't many molecules at low speed, and there aren't many at high speed. Most of the molecules, most of the time, have speeds somewhere in the middle. One other point about this distribution, we got it by jiggling the puck table at a constant rate of jiggling, and that's equivalent to keeping the temperature constant. Now, the 19th century physicist James Clerk Maxwell calculated the theoretical distribution for 3 dimensions, what we call the Maxwell Boltzmann distribution. I have it here in the dotted curve. They're not exactly the same shape, but that shouldn't surprise us too much. After all, this is for 2 dimensions, and that's for 3 dimensions. Nevertheless, they are broadly similar. And the important thing to remember is that they're both for models, a 2-dimensional puck model and a 3-dimensional theoretical model. Now, the key question is, do the molecules of a real gas behave in this way, jiggling about and producing a distribution of speeds, something like that? Well, I can certainly show you that they're jiggling about. Here, I've got a little device that can blow smoke ash. And I've got a television camera that looks through the microscope objective into this small chamber. Suppose I blow a small amount of ash into the chamber. You can see here the tiny particles of ash are certainly being buffeted about in all directions because they're colliding against many, many molecules. So I've got the jiggling. But that doesn't tell us anything about the distribution of speeds. In fact, it was over 50 years after Maxwell derived his theoretical curve before there were any experimental measurements that directly measured the distribution of speeds for real gas molecules. One of the first of these was by Zartmann in 1931 in the USA. Actually, we've told you quite a lot about this one in the unit. Let me just remind you of Zartmann's method. He's got an oven which he keeps at a constant temperature by heating it, and the gas molecules can escape through this tiny hole. And then there's another slit to collimate the gas molecules, and then this is the clever part of his apparatus. He has a rotating drum, and the idea is that he can smear out the molecules on the circumference depending on how fast they're going. In fact, I've got Zartmann's original paper here, and you can see what his results looked like. Along the bottom, he's plotting distance along the circumference inside the drum, and vertically the number of gas molecules. By the way, the reason there are 2 distributions is because they correspond to 2 different speeds of rotation of the drum. The one on the left will be the one for the slowest speed of rotation. But the important point I want you to notice is that the experimental points for a real gas agree very well with the theoretical curve which Zartmann calculated based on the Maxwell-Boltzmann distribution. To recap then, the 2-dimensional puck model gave me a distribution of speeds. The 3-dimensional theoretical calculation of Maxwell-Boltzmann also gave me a distribution of speeds. And the experimental evidence for real gases agrees very well with the Maxwell-Boltzmann distribution. We really do seem to be on the right track.
But you still might be a little bit worried about this whole idea of a rock-steady pressure being modelled by lots of individual tiny impacts. And not without reason, because on our two-dimensional model, the puck model, you notice the piston jittering around all over the place. But remember, one of the drawbacks with that model was that the pucks were quite large. They took up quite a large proportion of the space available. Now, we can do much better than that if we go to a three-dimensional model. Here, we're using ball bearings as the model molecules. And, of course, the volume of the ball bearings is now a much smaller fraction of the total volume available. And I think you'll agree that the piston is jittering a lot less than it was on the two-dimensional model. But while I've got this model here, in which the molecules aren't crowded close together, let me do one other test that wasn't actually possible with the two-dimensional model. Let me just mark the volume, first of all. And now I'll turn off. Now, at the moment, I've got 25 ball bearings in there. I'm going to add another 25, making a total of 50. And put piston back in again. Ease it down. Okay. Now, what difference is that going to make? Remember the equation. The equation is PV equals nRT. If the pressure's constant and the temperature's constant, because we're keeping the model jiggling at the same speed, R is a constant, then V must be proportional to N. N is the number of moles, or the number of molecules. So V should be proportional to the number of molecules. So what should happen here? Well, if I mark the new volume, I think you'll agree that there's been an expansion of about a factor of 2. In fact, it's looking so good that we have the feeling we ought to be able to extend this kinetic theory of gases into perhaps liquids and solids as well. Now, let me be honest, when we try to do that with numbers, when we try to do it quantitatively, we don't get very good agreement. And part of the problem is that we really are not correct in assuming there is no forces between the molecules of a liquid. There are intermolecular forces. And that causes a certain amount of difficulty. Nevertheless, the kinetic theory ideas can give us qualitative understanding of some phenomena. For instance, take evaporation in a liquid. Now, you must have noticed that if you leave a saucer of water lying around, nowhere near boiling point, then eventually all that water disappears, it evaporates. Or you must have noticed puddles on the floor after a rainstorm. Again, nowhere near boiling point, nowhere near 100 degrees C, but they evaporate. Why? Well, before you can start to answer that question, you've got to really have some sort of model of a liquid. And that really means that you've got to somehow model these intermolecular forces. And that's really too difficult on these three-dimensional and two-dimensional models. But perhaps we can get at least part-way towards that by considering just the surface molecules.
You see, a molecule in the body of the liquid is attracted to its neighbouring molecules equally in all directions, whereas a molecule at the surface is only attracted downwards into the liquid. And to escape the surface, a molecule has to overcome this downward force.
Well, a rough and ready way of modelling that force that has to be overcome is with this barrier. You can see that molecules aren't necessarily going to get through it absolutely perfectly. So this is going to represent the body of the liquid, and this the surface. And when we set the system going, we find that every so often a molecule gets through and is whisked away into the atmosphere. It escapes the surface.
And this is where our kinetic theory comes in useful, because I can think of a distribution of speeds for the molecules of a liquid, and it's going to be qualitatively similar to the distribution of speeds you've seen for gas molecules. And because there's a simple relationship between kinetic energy and speeds, I can also think of a distribution of kinetic energies. In fact, here I have a distribution of kinetic energies for liquid molecules. This is the low energy side, and this is the high energy side, and the number of molecules vertically. Well, it's a familiar shape, as you've seen before. Now think about this high energy end. The white area corresponds to the high energy end, and roughly speaking, I can think of them as being the ones that are likely to evaporate. Now think a moment about the effect of depleting these more energetic molecules. Well, the total energy, or the average energy of the total rather, is going to reduce. So that, well, what happens in practice is the molecules jiggle about and redistribute themselves and give us a new distribution of kinetic energies, which will look something like that. You see that the average kinetic energy has now gone down. And remember that there's a simple relationship between kinetic energy and temperature. So in other words, the effect of these molecules evaporating is a reduction in the temperature of the liquid, a cooling effect. And there's another thing we can see too. Let me just add one more curve corresponding to yet another temperature, a lower temperature. Now remember, this white area I can think of as being the molecules which have enough kinetic energy to evaporate, so that you can see very easily that as we go down in temperature, the number of molecules which have sufficient kinetic energy to get away from the surface rapidly diminishes. There is a very sensitive dependence between evaporation and temperature.